Hello students, I'm Azizi, Professor Electronics. In our previous session, we have developed a microprocessor-based system using the MCS 51 family member, that is 889C51 microcontroller. In our previous session, we have interfaced the external ROM, RAM and PIA with the microprocessor. And we have learned that what are the memory addresses for our microprocessor-based system. That is the memory map for the devices which we have connected with the microprocessor-based system. That is the address of the source code, address of the RAM and the address of the PIA. In this session, we will learn that how to write a program for our microprocessor-based system. First, we'll go through our previously developed circuit. Then we'll write a program for our microprocessor-based system. So let's start our today's session. And here we can find the circuit of our microprocessor-based system which we have developed during our previous session. Here we have used the microcontroller, that is 889C51 in microprocessor mode. As we have connected the external access pin of the microcontroller, that is pin number 31, with the ground. It means that if we connect the signal, that is pin number 31, external access with the ground, then the device will work as microprocessor and it will generate the address and data on port 0, and it will generate the addresses from A8 to A15 on the port 2. And here we can find two signals, that is read signal and the write signal on port 3.6 and port 3.7. Port 3.6 is write signal and port 3.7 is read signal. And here we can find two more control signals, that is PSEN, program stored enable, on pin number 29 and address latch enable on pin number 30. And we have connected the address latch enable signal with the IC, that is 74SC573, which is a 8-bit latch. And here we can find on pin number 11, that is latch enable, we have connected the ALE signal. First, the device, that is 889C51, will place the addresses on address bus, that is from port 0.0 to port 0.7. The device will place the addresses, that is from A0 to A7, and on port 2, that is from port 2.0 to port 2.7. The device will place the addresses, that is from A8 to A15 in microprocessor mode. After placing the address, that is from A0 to A7 on port 0, that is from port 0.0 to port 0.7, the device will generate a signal, that is address latch enable, to latch the addresses, and the addresses from A0 to A7 will be latched on the IC, that is 74SC573, which is a 8-bit latch. And we have also connected the address bus of the microprocessor with the ROM 1, ROM 2, RAM 1, RAM 2, EEPROM 1 and EEPROM 2, and PPI 1, that is programmable peripheral interface. And here we can find the memory addresses for different devices which we have connected with the microprocessor. Here we can see the ROM 1. The address range is from 0000H to 1FFFH, and the address range for ROM 2 is from 2000H to 3FFFH. And here we can find we have connected chip select 0 with the ROM 1 and chip select 1 with the ROM 2. And in our previous session, we have learned that what are the address ranges for chip select 0, chip select 1, chip select 2 and chip select 7. And here we can find the range for chip select 0 is from 0000H to 1FFH, and the address range for chip select 1 is from 2000H to 3FFFH. Similarly, the address range for chip select 2 is from 4000 to 5FFFH, and for chip select 3, 6000 to 7FFFH. And for the chip select 4, the address range is from 80000H to 9FFFH. And we have connected the chip select 0 with the ROM 1, so address range is from 0000H to 1FFFH. And we have connected chip select 1 with ROM 2, so the address range is from 2000H to 3FFFH. And here we can find we have connected two RAMs, that is random access memory, with our microprocessor based system. And the address range is same as ROM 1, that is from 0000H to 1FFFH and 2000H to 3FFFH. And we have used the same chip select, that is chip select 0 for RAM 1 and chip select 1 for RAM 2, but the source code ROM will be selected with the signal, that is program stored enable. And here we can find we have connected program stored enable signal with the output enable control pin of the ROM 1 and ROM 2. The microprocessor will automatically generate the signal, that is PSEN, to read the data from the source code, that is ROM 1 and ROM 2. And in our program, we'll read and write the data to the RAMs, that is random access memory, and EEPROM, that is electrically erasable programmable memory. To read and write the data from the RAMs and EEPROMs, the processor will generate two signals, that is read and write signal. And here we can find we have used the same chip select, that is chip select 0, as we have used for the ROM 1, and we have used the chip select 1 for the RAM 2 as we have used for the ROM 2, because the ROM 1 and ROM 2 will be selected from the signal, that is PSEN, and we'll use the signals, that is read and write, to read and write the data from the RAM 1, RAM 2 and EEPROM 1 and EEPROM 2. And here we can find we have assigned the chip select 2 to the EEPROM 1, and we have assigned the signal, that is chip select 3 to the EEPROM 2, and the address for EEPROM 1 is from 4000 to 5FFFH, and the address for EEPROM 2 is from 6000 to 7FFFH. And here you can find we have connected chip select 4 with the PPI 1, that is programmable peripheral interface, and the address range for chip select 4 is from 8000 to 9FFFH. Here in this circuit we are using two source code ROMs, that is ROM 1 and ROM 2. We are using RAM 1 and RAM 2. We are using EEPROM 1 and EEPROM 2. And here we have connected only one PPI with our circuit, that is PPI 1 8255A. And this device, that is 8255 PPI 1, has 24 IOs, that is port A, port B and port C. We can program this device as per requirement of our circuit. We can program this device to configure the port A as input or output. Similarly, we can configure the port B as input or output, and we can also configure the port C for input and output. But there is a difference between port A and port B. For port A, we can configure the port A as input or output as whole port. Similarly, port B can be configured as input or output as whole port. But for port C, the lower nibble and the higher nibble of the port can be configured as input or output. We'll learn that how to configure the ports, that is port A, port B and port C for different configurations, that is input and output ports. But first we'll learn that how to add some more ports to our microprocessor based system, that is how to add some more PIAs in our microprocessor based system. So let's see how we can add some more ports, that is 8255 with our microprocessor based system. And here we can find the extended version for our microprocessor based system. And here we have added two 8255 devices, that is PPI 1 and PPI 2 with our microprocessor based system. How we have added the second PPI circuit with our microprocessor based system. For this we have used another 3 to 8 line decoder, that is 74LS138. And here we can find the first 3 to 8 line decoder, that is U4 74LS138. And we have used the U12, that is 74LS138, the second 3 to 8 line decoder. And we have connected the chip select 4 signal generated by the first decoder, that is U4, with the input of the second decoder, that is U12, at pin number 4 and 5, that is E2 and E3. And here we can find the address range for the chip select signal 4, that is from 8000H to 9FFFH. It means if the signal, that is chip select 4, will be low during the addresses, that is from 8000H to 9FFH, then the second decoder, that is U12, will be selected because the chip select 4 will be low and E2 and E3 signal of the U12 will be low. It means the second decoder will be selected, and here we have connected the address, that is A2, A3 and A4 with the inputs, that is A, B and C of the second decoder. And we have connected the addresses, that is A0, A1 with PPI 1 and PPI 2. It means if all the addresses, that is from A0, A1, A2, A3 and A4 will be low, it means the first output of the U12, that is Y0, will be selected. If the address A2 will be high and address A3 and A4 will be low, then the second output of the U12, that is Y1, will be selected. And we have assigned the signal, that is chip select 4-0 and chip select 4-1 to PPI 1 and PPI 2. Here we can find we have connected the chip select signal of PPI 1 with chip select 4-0 and the chip select control for the second PPI, that is pin number 6, with the chip select 4-1. It means PPI 1 will be selected during the address, that is from 8000H to 8003H, and the second device, that is PPI 2, will be selected during the address, that is from address 8004 to 8007. And here we can find we have 8 outputs of the second decoder, that is U12, that is from Y0 to Y7, and we have used only 2 outputs, that is Y0 and Y1 for PPI 1 and PPI 2. Similarly, we can connect 6 more PPI devices with the same decoder, that is from Y2 to Y7. It means we can connect 8 PPI devices with the decoder, that is from Y0 to Y7. In this case, we can have 24 ports of 8 bits using 8 PPIs, and each PPI can handle 3 ports of the 8 bits, that is 24 bits. In this case, we can interface 8 PPI devices with our microprocessor based system using the decoder, that is 74LS138. Because the address range for chip select is 8000 locations, that is from 8000H to 9FFH, and each PPI device occupies 4 addresses for port A, port B, port C and for control word register. So if we will divide the address range, that is 8000 with the 4, we can interface 2000 PPI devices for the chip select, that is chip select 4, between the address range, that is from 8000 to 9FFFH. And here we can find we have connected 8 dip switches with the PPI 1, that is on port A, from port A0 to port A7, and we have connected 8 LEDs on port B of the PPI 1, that is from port B0 to port B7. And here we can find we have used a Darlington driver, that is UL-N2803, to drive all 8 LEDs. Now we'll write a program to read the status of the switches from port A, and we will write the status of the switches connected on port A to the port B of the PPI 1. Before writing a program, we will learn a new instruction to work with the microprocessor based system, and we'll also learn that how to configure the device, that is PPI 8255, for different configurations of input and output for port A, port B and port C. To write the program for the microprocessor based system, we'll use instruction, that is MOVX, and here we will learn that how to use instruction, that is MOVX. As we have connected the device, that is 8255 PIA with our microprocessor based system, and each 8255 interface has 3 ports, that is port A, port B and port C, and it has another internal register which is called control word register. The address for the port A is 0H, the address for port B is 1H, The address for port C is 2H and the address for control word register is 3H. As we have connected the chip select signal of the 8255 device with the chip select 4, and we have learned that the range of the chip select 4 is from 8000H to 9FFFH. It means 8000 addresses, that is from 8000H to 9FFH. In this case, the address for the port A will be 8000H and the address for port B will be 8001H and the address for port C will be 8002H and the address for control word register will be 8003H. The internal register, that is control word register of 8255, is used to configure the ports, that is port A, port B and port C for their different configurations for input and outputs. And we'll learn that how to program the control word register for different configurations of port A, port B and port C for their inputs and outputs. To read and write the data from the port A of the 8255 device, the address of the port A is 8000H. We will use the instruction, that is MOVX, to read the data from the port A or to write the data to the port A. Here we can find that how to use the instruction, that is MOVX, that is move external, that is MOVX accumulator @DPTR. First we'll move the address of the port A to the data pointer, that is DPTR. So here we have written, that is move DPTR, hash 8000H. It means move the address of the port A to the data pointer. And here we have written that MOVX in accumulator @DPTR. It means that move the contents of the address, that is from 8000H to the accumulator. It means read the data from the external device to the internal register of the microprocessor, that is accumulator. In this case, the microprocessor will automatically generate the signal, that is read signal, and the read signal will be low and data will be moved to the internal register of the microprocessor, that is accumulator. Similarly, if you will write the instruction, that is MOVX @DPTR, A, it means move the contents of the internal register of the microprocessor, that is accumulator, to the external device, and the address of the device is given in the DPTR, that is data pointer, which is 8000H. In this case, the contents of the internal register of the microprocessor, that is accumulator, will be moved to the external device, that is port A of the 8255. If you use the instruction, that is MOVX, in this manner, that is MOVX @DPTR, A, it means move the contents of the internal register of a microprocessor, that is accumulator, to the external device, that is port A of the 8255. This operation is the write operation and the microprocessor will automatically generate the signal, that is bright bar. And here we can find the pin number 36 of the 8255 is write signal. If this signal will be low, then the data will be returned to the port A because the address of the port A is given in the DPTR. So we'll use the instruction, that is MOVX, to read the data from the external device or to write the data to the external device. Now we'll learn that how to configure the control word register for port A, port B and port C for their different configurations for input and outputs. If we'll go through the data sheet of the 8255 PIA, we can find the control word register, and here we can find different bits of control word register, that is from D0 to D7. And here we can find if the status of the bit, that is D0, will be 0, then the port C lower will be output, and if the status of this bit will be 1, then the port C lower will be input. Similarly, if the status of the bit, that is D1, will be 0, then the port B will be output, and if the status of the bit, that is D1, will be 1, then the port B will be input. For the bit, that is D2, if the status of the bit, that is D2, will be 0, then the device, that is 8255, will be configured in mode 0, and if the status of the bit, that is D2, will be 1, then the device, that is 8255, will be configured in mode 1. And for the bit D3, if the status of the D3 will be 0, then port C upper will be output, and if the status of the D3 will be 1, then port C upper will be input. For the bit, that is D4, if the status of the port D4 will be 0, then the port A will be output, and if the status of the bit, that is D4, will be 1, then port A will be configured as input port. And here we can find two bits, that is D5 and D6 for the mode selection. If both the bits will be 0, then the mode 0 will be configured. If D5 will be 1 and D6 will be 0, then mode 1 will be configured. And if the bit, that is D6, will be 1, then the mode 2 will be configured. And here we can find mode 0, mode 1 and mode 2, that is basic input output, strobe input output, or bidirectional bus. And for the bit, that is D7, here we can find mode select flag. If this bit, that is D7, will be set as 1, then the device will be active, and if this bit will be 0, then the device will be deactivated. And here we can find a control word for control word register. D7 is 1, it means device is active. D5, D6 bits are 0, it means mode 0 is selected, which is basic input output mode. D4 bit is selected as 1, it means port A will be configured as input port. The status of the bit D3 is 1, it means the upper nibble of the port C will be configured as input. And the status of the bit D2 is 0, it means mode 0 will be selected. And the status of the bit, that is D1, is 0, it means that port B will be configured as output mode. And here we can find the bit, that is D0, is also 0, It means that the lower port C will be output. Similarly, we can find different configuration words for port A, port B and port C for their different input and output configurations. And here we can find different control words for 8255 PIA for mode 0 configuration. Here we can find the control word 0 because to activate the device we have to set the bit that is D7 as 1. So the control word will be 80. In this case we have the control word that is 82. For control word 80 all three ports will be output. That is port A will be output, port B will be output, port C lower will be output and port C upper will be output. Similarly for the control word 82 we can find port A is output, port B is input, port C lower is output and port C upper is output. For control word 84 we can find port A is output, port B is output, port C lower is output and port C upper is input. For control word 90 we can find port A will be input, port B will be output, port C lower will be output and port C upper will be output. Similarly, we can find different configuration words for port A, port B and port C for their different configurations of input and outputs. We will use the configuration word that is 90 in our program. Here we can find the configuration word that is 90. In this case, the port A will be input and the other two ports that is port B and port C will be output. So we'll use the configuration word that is 90 in our program because we have connected the switches on port A and we have connected the LEDs on port B. So we will read the status of the switches connected on port A and we will write the status of the switches on port B. Now we'll start writing our program to read the status of the switches connected on port A of the first PPI. And we'll write the status of the switches on port B of the first PPI. And here we can find the address of the port A of the first PPI is 8000H and the address for the port B for the first PPI is 8001H. And the address for the control word register for the first PPI is 8003H and the control word will be 90 to make the port A as input and the other port that is port B and port C as output. So let's start writing our program. And here in Microvision, first we'll go to the project, new Microvision project, and here in the folder that is microprocessor programs, we'll select the folder and here we'll assign the name to our project that is SBC_1. So here we will write OK, save. Now we'll select the microcontroller. OK, select. Target 1, right click. Option for target, target 1. The crystal oscillator frequency is 12 MHz. We'll go to the output and we will select the checkbox that is create hex file. OK. Source group 1, right click, add new item to the group source group 1. And here we'll select ASM file and we'll assign the name that is SBC_1. OK, add. And from here we'll start writing our program. First we'll assign the comments. Here we have assigned the name to our project that is microprocessor project 1. And now we'll define some variables in our program. And here we will define the variables that we will use in our program. And here we can find from the circuit that is address for port A is 8000H, address for port B is 8001H, address for port C is 8002H, and the address for control word register 1 is 8003H. So we'll use these addresses in our program. So here we will write that is port A_1 EQU 8000H, port B_1, that is the port B for first PPI, EQU 8001H, port C_1 EQU 8002H, and control word register _1, that is control word register for PPI 1 EQU 8003H. Now we'll define the constants for our program, and here we will write that is control word _1 EQU, that is 90H, and here we will write the directives for our program, and here we will write that is org 0000H, and we will write that is jump ini underscore r, that is initialization routine, and we will write that is org 0030H, that is start writing the initialization routine from the 30H location, and here we will write that is ini underscore r using colon. First we will initialize the control word register by moving the value that is 90H to the control word register. So here we will write that is move dptr comma hash control word register underscore 1, and we will write that is move accumulator comma hash control word underscore 1, and we will move the value of the accumulator to the address that is 8003H. So here we will write that is MOVX @dptr comma A. Here we have initialized the control word register for port A as input, port B and port C as output. And now we'll write our main program, and here we will write that is main using colon, and now we'll read the status of the switches connected on port A of the 8255 PIA1 to the accumulator. So we'll write that is move dptr comma hash port A underscore 1, and we will write that is MOVX accumulator @dptr. It means move the contents from the address in dptr to the accumulator, and we will write that is move dptr comma hash port B underscore 1. We have moved the address of the port B of the PPI1 to the dptr, and we will write that is MOVX @dptr comma A. After moving the contents of the accumulator to the port B, our program will jump back to the main. So here we will write that is jump main. Here we have completed our first program for the microprocessor based system, and now we'll complete our program by writing the end instruction. Now I'll compile our program and we'll check the result of our program on Proteus simulator. Here we can find 0 error, 0 warnings. And now we'll download the hex file to the microcontroller, because in Proteus we cannot download the program into the ROM. But in real world circuit we'll download the program to the ROM 1. But here in Proteus we'll download the hex file to the microcontroller. Right click, edit properties. And here in the folder that is microprocessor programs, objectives, and here we have the hex file that is sbc_01.hex. Okay, and now we'll run the simulation, and here we can find the status of all switches connected on port A is 0, and the status of port B is also 0. If we'll switch on the first switch, our program will read the status of the switches connected on port A and will send the status of the switches on port B, and here we can find the status of port B not is 1, and here we can find the LED 1 is on. Similarly, we can select the other switches. So here we have written our first program for the microprocessor based system, and we have learned a new instruction that is MOVX. Similarly, we can read and write the ports of the PPIs connected in our circuit by using the same instruction that is MOVX. The other techniques for the assembly language programming is same as we have learned in our previous sessions. In this session, we have learned that how to work with the microprocessor based system. This lecture was the last lecture of our course, that is learning assembly language programming techniques using MCS 51 family. If you have any question or require any assistance for this course, please email me at electroeducators@gmail.com. See you in next course. Thanks for watching this semi-language programming course. We hope that you find this course very helpful to learn semi-language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electroeducators as soon as it goes up. Electroeducators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.